Hey everyone, you ever stop and think about how your phone just knows it's you, like instantly? Or how a self-driving car can spot someone on the sidewalk? Well, today, we're going to pull back the curtain on the magic behind all that. We're talking about how machines are finally learning to see.
I mean, it really all comes down to this one big question, right? How in the world do you teach a computer to see and understand what it's looking at, just like a person? Because it's not just about recording a bunch of pixels. It's about knowing what those pixels actually mean. Okay, think about it like this. How do you recognize a cat? You don't just see the whole thing in one go, right? Your brain is way smarter than that. First, it picks up on the simple stuff. Basic shapes, some lines, some curves. Then it starts putting those pieces together to form more complex things like, oh, that's an eye, that's a nose, and that's a pointy ear. And finally, bam, it assembles all those parts and your brain goes, yep, that's a cat. It's all about building up from the simple to the complex. And believe it or not, that exact same process, that way our own brains work, is the inspiration for how we're teaching machines to see. It's pretty cool. We're basically building an AI that mimics our own vision. And that brings us to the star of the show, convolutional neural networks, or what everyone calls CNNs. They are special kind of AI that are designed to do exactly that, to copy that layered, step-by-step approach our brains use to build a full picture from just simple little patterns.
So, okay, how does a CNN actually take its first peek at an image? Well, it all starts with a process called convolution. And this all happens inside its most important part, the real workhorse, the convolutional layer.
Now, the whole job of this convolutional layer is to be like that first step in our own vision. Its only goal is to scan the image and find all the basic, raw features. It's not trying to find a cat's face just yet, no. It's just looking for the little building blocks, the lines and textures that could, maybe become a cat's face later on.
And to do this, it uses a neat little tool called a filter, sometimes also called a kernel. The absolute best way to picture this is to think of it like a tiny digital magnifying glass. But here's the twist. Instead of just making things bigger, this magnifying glass is a specialist. It's trained to hunt for one very specific pattern, maybe a straight vertical line, or a sharp corner, or even just a certain change in color. So here's how it actually works. The filter, our little magnifying glass, slides over a small patch of the image. It does some quick math, basically asking, hey, do the pixels under me look like the pattern I'm looking for? The answer comes back as a single number. A high number means yes, big match. A low number means nope, nothing here. And then it just keeps doing that. Slide, check, all the way across the image. What you get at the end is a brand new image called a feature map, which is basically a treasure map that lights up everywhere that specific pattern was found. Pretty clever, right? Okay, but let's be real. A map of just a bunch of edges isn't going to help us find a cat. The real power, the secret sauce, is in what happens next, how the network takes all these simple little clues and starts to build a much bigger picture. And this is where the magic really happens. It's all about hierarchy. You see, a CNN isn't just one of these layers. It's a whole stack of them, one on top of the other. So those treasure maps from the first layer, the ones with all the simple lines and colors, they get handed off to the next layer. And that second layer's job is to find patterns in those patterns. It starts combining simple edges to spot things like corners or simple textures.
And this is a perfect example of what I'm talking about. Over on the left, you can see what those early layers are hunting for. Really simple, basic stuff, right? Lines, colors, gradients. But then, look over to the right. This is what the deeper layers start to see. They've learned how to take that simple stuff and combine it into way more complex things. You're seeing textures, shapes, things that look like honeycombs or scales, or even the beginnings of animal fur. So, after the network has pulled out all these features from the tiniest lines all the way up to complex textures, it's got a whole lot of information. Now it needs to start making sense of it all and, actually make a decision. One of the first things it has to do is, simplify things. As you go deeper, you get a ton of data, just a massive amount of detail. So we have something called a pooling layer. Its job is to shrink things down, to compress all that information by focusing only on the most important bits. It's a way to keep the strongest signals while making everything faster and more efficient. Let me show you exactly how this works with a super simple example. So imagine this 4x4 grid is one of our feature maps. Each number just represents how strong the signal is for that feature. Now, a really common trick called max pooling is going to look at this grid in little 2x2 squares.
And here's what it does. For each of those little squares, it just looks at the 4 numbers and picks the biggest one, the maximum value. That's it. It keeps the strongest signal and just throws the other 3 away. And just like that, our 16-pixel map shrinks down to a tiny 4-pixel map. We've lost a lot of data, but we've kept the most important piece of information from each little area.
I mean, think about that. That one simple step just tossed out 75% of the data. But what's really, really cool about this isn't just that it makes the network faster. It's that by focusing on just the strongest signal, the network starts to care less about the feature's exact location. It just cares that the feature is there. So if a cat's ear is tilted a little bit or in a slightly different part of the picture, the network doesn't care. It can still recognize it. It's learning to generalize, which is a huge deal. All right, so after all that back and forth, convolution pooling, we're left with a bunch of really dense, compact feature maps. Now, before we can make the final decision, we have to do one last housekeeping step. We use something called a flatten layer, which does exactly what it sounds like. It takes that whole stack of 2D grids and just flattens it out into one single long line of numbers. And that long line of data gets fed into the grand finale, the fully connected layer. This is basically the brain of the whole operation. It takes a look at that final combined evidence. It sees the signal for pointy ears, the signal for whiskers, the signal for furry texture, and it puts it all together to make the final judgment call. It spits out a probability, something like, okay, based on everything I've seen, I am 98% sure that's a cat. Now, I know this whole process might sound a little abstract, filters and pooling and flattening, but this exact process is the engine driving some of the most mind-blowing tech that you and I use literally every single day. So why should you care? Well, CNNs, that's what's unlocking your phone with your face. It's what's helping doctors find tumors on medical scans, sometimes even better than human experts. It's what gives a self-driving car the power to see a stop sign or a person crossing the street. Tagging your friends in photos? Helping a robot find its way around a room? Yep, it's this stuff. It is absolutely everywhere. And that really leaves us with a pretty wild thought, doesn't it? We've managed to teach machines how to see, how to recognize the world visually. So, if they've already mastered sight, what's the next big thing they're going to learn to understand? Makes you think. Thanks for joining me.